Hello, so this is a continuation of the previous recording, and we started to discuss there about how we're going to set up everything to render the tiles in the elevation producer. So last time I started to kind of mention a few things about this. We are going to replace the frame buffer from OpenGL with a render pass in WebGPU. Now, you want to be able to do the rendering from multiple threads at the same time, which means imagine first you would share the render pass. So you would have a render pass targeting a fixed texture. We mentioned already that the idea was to render into a fixed texture, and then when we're done with rendering the tile, we would copy what was written into the texture into the appropriate layer of our tile storage, which is the texture to the array. And so if you were to do this from multiple threads and using a single render path, what would happen exactly? You would have a render path targeting your texture, and you would request the execution of a pipeline. So you would be rendering something to that texture, and then you would have another request to your queue to copy the content of this texture into a given layer, which is another slice, if you want, of the texture to the array. And if you do that, in fact, I have no idea what's going to happen. Because from each thread, you would submit first a render pass in your. You would use your command encoder to encode a render pass, and then the same command encoder you would submit the texture copy operation. And then with that, you would create a command buffer, and you would submit this command buffer to the queue. But what if, for instance, the queue is able to take those two commands buffer, see that you have two render pass requests, and after that, two texture copy operation, but it could still maybe decide to execute the two render passes one after another, or even worse, both somehow concurrently writing to the same texture, and only after those two are executed, execute the two copy operation. So if this were to happen, you would get complete garbage because you don't really know what you're going to copy into the first layer or what's going to be copied into the second layer. It could be exactly the same data, and that's not what you want. So to be safe, and I think this is the most logical thing to do, you really need to separate the resources that you use on those different threads, which means you need a dedicated render path per thread. And also, your render path is going to use a dedicated, a dedicated target texture. This target texture should not be the same. You should have one per thread. This is in fact what I was trying to discuss a little bit here up to this point, where I thought that maybe it's better to have per thread textures. The only thing maybe is you have noise texture. So I've already shown that somewhere in there, but we're going to recreate that. So in our elevation producer here, at the very beginning, there is a function which is used to create this noise texture, which is also a texture to the array. So you have 6 layers in this one. And this texture, in fact, you're going to, I think we can just share that between all the threads because it's not going to be modified at any time. It's just an input. And so what I've been discussing there is we can provide the texture as part of a binding group layer, a binding group 0. There is another thing which we can provide as part of this binding group, which is residual texture. This one, it's going to provide the coarse parent texture. So let me try to get back to this one. You see, let me think. No. Wait. No. It's not the residual texture we want to put here. It's the coarse level simpler. I don't know why I was writing that. Yeah, I think this was the initial idea, but it didn't went this way. Let me just check that. Yeah, so here is how we are setting up things in the end. We have a full node, which is a render node, which is going to set up this planned up simple shader, which is not implemented yet. Actually, I also need to do that. And so in here we define two different binding groups. So the group 0 is going to provide a simpler texture. Actually, I don't really have any idea yet what this is going to be, but we don't really need to know now. Then it's going to provide a texture to the array, the first one, which is the noise texture, and then another one, which is going to be the parent coarse texture. The idea with the second one is you need to provide access to the parent tile for the tile that you're going to build. Parent tile is basically the one which is 4 times bigger. In space, size are the same. And the thing is, to access that, you need a specific layer in one of the available texture to the arrays, which are used for the complete storage of all those data. But the thing is, there is only a limited number of such texture. Typically, the maximum number of layers that you can have for a single texture to the array is going to be 256. But you could have setup. Let's just see that in the initial implementation. If you were to look at those terrain symbols, well, we have those Proland elevation, okay, which is an elevation producer. This is going to use a tile cache, with which itself is going to use a GPU tile storage. And the number of tiles that you want to be able to store in there is 512 in this case, which means you're going to use 2 textures to the arrays to provide all the layers that you want to be able to store. This number can increase a little bit, but the number of textures that you will get in the end is pretty limited. It should be like 1 to 8, or maybe 10 texture max. So the idea I had was to provide this first binding group. You can in fact write a fixed number of binding group. Create a fixed number of binding group. Each binding group should provide the same noise texture, and then here it should provide one of those textures that you have available in the texture storage. So that's what we do exactly here. We define this group, and then we retrieve the storage as a GPU tile storage, and we figure out how many textures we have here used for storing the tiles. And we're going to create a binding group corresponding to the group 0, so the first group defined here, where we provide a linear sampler for now, and then we provide a texture binding on the noise texture, another texture binding on the texture corresponding to this index. And yeah, you just keep track of all those bind groups, and then you don't need to allocate any bind group dynamically anymore. What's going to happen is whenever you want to create one of those tiles, you will figure out, okay, I am creating this tile, so the parent is this one, and the data for the parent tile is stored on the texture number 5. And when you have this figured out, what you just need to do is, okay, take the bind group number 5 for binding 0 and just bind that before I do the rendering for the current tile. And so you don't need to create those bind groups per thread, because this, again, are not changing. The data that you're binding is not changing per thread. It's fixed, but you still have a few possibilities, a few different indices. So that's it for the first bind group. And then you have the second bind group, where we're going to provide a uniform buffer and a residual texture. So what I was writing here was not quite correct. I think I was mixing residual texture and parent coarse texture. Anyway, so in this second bind group, you want to provide the uniform data which you are going to collect for the rendering of each tile. But this part is something that you want to do per thread. So this bind group here, you can't really allocate that globally. You really need to provide that per thread. So let's have a look at the structure that we created for that. We have now defined this thread data structure, which is going to contain a uniform buffer on this uniform data. And this uniform data is just those list of 4 uniform vectors corresponding to those uniform that we had in the OpenGL version. So this is part of the thread data. Also, the dem texture here is the target we're going to use to do the rendering in our render pass. And the render pass itself is going to be thread specific. And also the residual texture, where we're going to upload some residual data per tile again. You want to have that separate per thread. And additionally, there is this bind group, the bind group for the group number 1, which is going to be created per thread. And so, yeah, then we have this key function, get or create thread data. This one is going to use this thread index, which I think I quickly mentioned in the previous recording, which was an initial idea from here, which is that you can get an index for a thread which is incremented progressively from 0. And when you have that, what you need to do is to access a fixed static slot for your thread data. And this static slot, the key thing here is it's coming from a static vector, which is, well, not really static, but a vector which is initialized at the start when you create your elevation producer, and then it's not modified anymore. So we have that in there. It's not even a vector, it's just an array. So you have an array of pointers to this thread data, and you have a fixed size, which is the maximum number of per thread that you want to be able to use. So that's going to be a fixed value for me, like 32. Probably I'm never going to use that many worker threads, but yeah, we could just change that if we need more working power, because the key thing is we're just storing here a reference pointer on this data. We're not actually allocating anything yet, because this pointer will be null by default. And the logic after that is you try to access this slot and you actually check if it's null. If it's null, then since you are on the thread where you actually need to perform the work, you need to initialize this slot. So you create a new data structure for the slot, and then you start initializing what you have as entry in this. So the residual texture, the DEM texture, the render path itself, which is going to render to this DEM texture target, and then also this binding group number 1. And yeah, to create this, you're going to use the uniform buffer that you have for this very specific slot. You attach that as a uniform buffer in the fragment shader. And you also provide a texture binding on the residual texture that you also created as part of this slot. So at this point, all this data is contained for the given thread, and you don't need to worry about synchronization anymore at all. And you just then return that slot. And of course, if it's already initialized, you don't lose time reinitializing anything. So that's great. And keep going there. From there, you get access to the free data, and one of the first things you're going to do is to actually retrieve the uniform buffer and start populating those vector elements. So you have the first one here, I guess all the unit point something. Another one in there, and there, and there, and so on. And yeah, concerning the residual tiles, this is supposed to be how you use the elevation producer, really. But you can still use that without residual tiles producer. And so for now, I'm just disabling this part. This is what I mentioned, in fact, a bit before or a bit after. Yeah, this part here. We don't really need to support that for now. If when later I will get to this part, I will need to implement the CPU tile storage, because for the residual data is stored on the CPU side and it's uploaded for each rendering every time. So you get the data from the tile, and then you're going to upload that onto your residual texture just before using this residual texture in the shader. So for now, just disabling this part. Then you have another part for the noise, and eventually you would just update the uniform buffer, so request writing to the corresponding buffer on the GPU. And after that, well, that's where I stop, because where did I realize that exactly? It was, in fact, when I was setting up no, not really even there. Here, creating a render path, okay, but then on the shared part, where's the constructor? Here, you create a render node where you want to apply this simple program. And when I was writing this part, I started to think, hey, come on, why on earth are you doing that? Because you are setting up here the brain state, you want to disable that, the depth state, you also want to disable that, and you're going to provide a vertex shader and then a fragment shader, but your vertex shader is really doing nothing because you want to consider that you're doing a full screen quad align rendering, and all that to update some content into texture, which is not really used as displayable texture at that point. So if you think about it, you don't use a render path to do that. You use a compute path. And yep, so that's where I thought, okay, I'm working here with render node and render paths, but I really want to change that into a compute path and a compute node. So yeah, my attention shifted to this other direction at this point. And I have a few additional things that I didn't mention here concerning that tree and the evolution of the dynamic buffer. But then, as I said, while preparing all that, I started to think, okay, I need to move to a ComputePipeline. So I think this is, yeah, this is the next interesting part, but I think we should not move to this right now, and we're going to keep that for the next session. Maybe just a couple of final notes, not directly related to this implementation here, but I have also updated my dynamic buffer because, in fact, I was using that to control my camera. Let me try to recollect my memories. Initially, yeah, in my WebGPU camera, I was providing this uniform data. It was an update compared to the initial version of the buffer provider, which was already containing a buffer by itself. But for the camera, I decided to move to this structure, and then I figured out, okay, in fact, this was breaking many of the examples that I had built before. So I had to update the buffer provider to kind of be able to access what I'm defining here, this data. But the point is, this data depends on the uniform data, which is something that is only defined in the subclasses. So when you are in the buffer provider, you don't really know what's going to be the structures. You don't really know how to, well, you can't even create this as part of the parent class. So I decided at that point, okay, but why would I not introduce a parent class into the dynamic buffer itself? So this was the idea with the update here. Yeah, you can have now, let's just check out dynamic buffer. So you have a dynamic buffer here, which depends on the template class, but the parent dynamic buffer base here doesn't depend on anything. It's just going to define a buffer and a vector on the CPU side, storing the same data on the GPU and the CPU. And yeah, you construct that. All you need to know really is the size of the buffer, final size. So you don't really need to have the structure itself. And in fact, I pushed that a little bit further afterwards because I have introduced also the GPU buffer. And the GPU buffer is a class defined just before here. And this one is really just encapsulating a buffer, pure GPU buffer. The difference is we are not adding the CPU side vector yet. So this CPU side vector, the data, is only introduced in the dynamic buffer base. You have that stored here. Because yeah, I have other cases now where I really need to access a GPU buffer, and I need to provide some utilities around this buffer, but I don't want at the same time to allocate the corresponding vector on the CPU side, because that's not the point in some cases. So that's where using this GPU buffer is handy. Okay, and as I said, these are small details, but we should probably stop this recording here. And in the next part, we are going to move to compute shader, which is very interesting, I think. So see you next time, and yeah, thanks for watching. Bye bye.